Hello and welcome. In today's lesson, we will talk about connecting the factors of a quadratic relation with its x-intercepts. In order to better understand this, I would like to explain the similarities and the difference between the words quadratic function and a quadratic equation. So here are the algebraic representations of them. As you can see, a quadratic function is represented by an equation. Whenever you have an expression equals another expression, then we say that we have an equation. Similar to this, we're going to say that the quadratic equation is also represented by an equation. I want you to look at both of them and try to see the difference between the two equations. Now, in a quadratic function, in one side of the equation we have y, and then ax squared plus bx plus c in the other side. Whereas in a quadratic equation, in one side we have 0, and then ax squared plus bx plus c on the other side. So what does this mean? The explanation has the roots in the real meaning of the term quadratic function. When we say a quadratic function, what we mean is the equation of it. So the equation of a quadratic function. For short though, we call it a quadratic function. Now when we talk about the quadratic equations, we mean the zeros of a quadratic function or the x-intercepts of a quadratic function. So we have agreed on these two definitions so that we won't confuse them with one another. So what is the meaning of this equation, and what's the meaning of this equation here? So an equation and a function practically. So how are they different from one another? Suppose that we have some quadratic relation, and the parabola that I drawn here represents ax squared plus bx plus c. Now, whenever we have an equation, we can find solutions to the equation. And in this case, we will say that any point that is on the graph of y equals ax squared plus bx plus c will have coordinates x and y. And if you substituted these coordinates x and y into the equation y equals ax squared plus bx plus c, then the left side will equal the right side. What that means is that we have one solution here, one in here, one in here, and I don't need to continue any longer because by now we can see that we have an infinity number of ordered pairs that satisfy the equation of a quadratic function. So we'll say there is an infinite number of solutions. Okay? Whereas in a quadratic equation, we don't just look at all the points, but we only look at the points where y equals ax squared plus bx plus c equals 0. Now recall what used to be here on this side of the equation for the function. Here we used to see the variable y, and the variable y here is made a 0. Now think about where the y variable is 0, at what points. So we're going to say that the y variable is 0 only at the points that are on the x-axis. So the only points that are on the x-axis are the x-intercepts. So in a quadratic equation, this will be the zeros or the solutions to this equation. So we have a limited number of solutions. So we're going to leave it here for now because we'll discuss this to more extent very soon. So limited number of solutions. Okay? So one way to find the zeros of quadratic equation is to graph the quadratic equation and find its x-intercepts. And for a quadratic function, you graph it and you can find all the ordered pairs. Now, the x-intercepts are what we call the zeros of a quadratic equation or the real roots. Real roots are the points where the parabola intersects the x-axis. And these are the points where the y value equals 0. That's why they're also known as the zeros of the quadratic equation or quadratic function. The x-intercepts are also known as the real roots or the real solutions. Now remember that a quadratic equation can have two x-intercepts, like in the following example here. Okay. So here we have two x-intercepts at each point in here. But a quadratic function can sometimes intersect the x-axis only at one point. And sometimes it decides to intersect the x-axis at no points, which means no x-intercept. Now in this case, we're going to say that here we have two distinct roots. Distinct means different from the one another. In here, we're going to say that the quadratic function has two equal roots, okay? And then in the last one, we're going to say that there are no real roots. So I will explain more specifically as we move on to the examples. So we are going to solve the quadratic equations given by using the factoring method. To solve by using the factoring method means to factor the quadratic expression first. So we are trying to factor in here the expression x squared minus 2x minus 3. So the factored form of it would be, you write x in here and x in here, okay? And then you have to figure out the two numbers that have the sum of -2 and the product of -3. The two numbers will be -3 and +1. So to solve a quadratic equation by factoring means to factor the expression first. And then we have to find out the x values that will make the expression 0. So since here we have a product of two factors, we're going to say that if one of the factors is 0, no matter what the other factor would equal, then the product will equal 0. And same applies to the other factor being 0. If we multiply it by x minus 3, which is the first one, then the product will be 0. We know that multiplication by 0 also gives the answer of 0. So therefore, we're going to say that to find the zeros of this equation, we make each factor equal to 0. So we're going to say if x minus 3 equals 0, the product will be 0, or if x plus 1 equals 0, the product will be 0. So that will happen at x equals 3 and x equals 1. In this case, we will say that the quadratic relation will have two real distinct zeros. Negative ones here. Sorry. So here is -1 and here is +3. So the graph of this relation would look somewhat like this. That's not very accurate. It's just sketching, by the way. And we're going to say that there are two real, and we're going to say distinct roots because they are different from one another. So we're going to take a look at the next example. So in the next example, we have -2x squared plus 4x minus 2 equals 0. Remember that when we are solving a quadratic equation, it is very important we first reduce the coefficients to lowest possible. And you probably notice that in here we have a -2, a +4, a -2. These are all even coefficients. Whenever you have even coefficients, you can factor at least the number 2. And since we're starting with a negative in here, then we're going to say that we need to factor the negative as well. Now, only in quadratic equations, which means only when we have 0 on the other side, we can divide both sides of the equation by the common factor in order to simplify. What does that mean? So we can divide by -2 every term in the equation, and that will result in x squared minus 2x plus 1 equals 0. Okay? Now, we are thinking we're ready to we're ready to solve now, but we need to factor because we have to solve by factoring. So here go my two sets of brackets. I start with x and x. And then I have to think of two numbers that have the product 1, the sum -2. When the product is positive, the two numbers must have the same sign. But since the sum is negative, then the same sign means that they're both negative. Therefore, we're going to say we have x minus 1 and x times x minus 1. So in this case, we're going to say that either x minus 1 equals 0 or x minus 1 equals 0. So that gives x equals 1 or x equals 1. So as you see here, both solutions are same number or equal same number. And this is the reason why we call these two solutions two equal roots or two real equal roots. Okay? So we're going to write two real equal roots. Now, what does the graph of an equation with two real equal roots look like? Remember, if you write x minus 1 times x minus 1, it's the same as if you wrote x minus 1 squared. And that would be a simple translation by 1 unit to the right. So it would look actually exactly the same as the graph of this parabola right here. Okay? Now, let's take a look at the third and the last example. So in this example, we have x squared plus 10x plus 21 equals 0. So in this case, we're going to say that we have x, then x equals 0. So what we have in here is x plus 7 and x plus 3. So these two will add to 7 and will multiply to 21, right? So therefore, we're going to say that x plus 7 equals 0 or x plus 3 equals 0. And we have x equals -7 or x equals -3. So in this case, we're going to say that the equation will have two real distinct roots. Okay? Now, you're probably wondering, okay, what do the parabolas that have no roots look like? Well, here's a parabola with no roots, right? So what would the equation then look like? So we are going to discuss these to more extent when we use different, or when we learn different ways, a different method of solving quadratic equations. Now that we understand the meaning of the zeros of a quadratic relation and the difference between quadratic function and quadratic equation, we'll move on to learning how to graph a quadratic equation by using its zeros. So I wrote a set of steps in here that we need to follow in order to go through the process of graphing by using the factors. So I'm going to box it up right here for us. And we're going to take a look at a couple of examples together. It's going to be easy, all right? So we're going to start with the first example. The first example is y equals x squared minus 2x minus 3. Okay? And here I go again with great embarrassment. I have to admit that I've made a typo in here, which I will fix here. And I will pretend that it never happened. Okay, here we go. So this is the equation. And in order to graph by using the factors, guess what we're going to do first? We are going to, well, first of all, we always have to take care of the greatest common factor if necessary. Let's check. Excuse me, gosh. And we don't have a common factor here. So the next step is factor the equation of the given quadratic function. So let's factor. And we have, sorry about that, y equals brackets, 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 x minus 3, x plus 1. And now we're going to say, what are the zeros in here? Well, the zeros will be x minus 3 equals 0, or if x plus 1 equals 0. So that will happen at 3 and at negative 1. And you know what I'm going to do? I am going to plot the zeros in here. I drew the axis. I don't have a scale, but I'm going to eyeball it for now. So this is negative 1. This is 0. The x and the y axis. We have 1, 2, 3. So this is the second 0. And now I'm thinking, I need to draw the graph of this quadratic, okay? And in order to draw the graph, I need to know two important things. Number one, the vertex, and number two, the step pattern. Now for the step pattern, we don't really have to worry here. The step pattern, because A is 1 through 5. So the key will be, how do we find the vertex? Well, think about where the vertex is. The vertex will always be right in the middle between the x-intercept. So if these two are the x-intercepts, then the vertex must be somewhere in here, because it's right in the middle of the parabola. And parabolas are symmetrical shapes, right? So I'm going to draw that axis of symmetry here with a very thin line here. Okay, so where is the, or what is the x-coordinate on the axis of symmetry? So we're going to say that the x-coordinate is in the middle, or halfway between negative 1 and 3. And from the graph, we can easily see it. That is at x equals 1. So how would you find this algebraically? So once you found the zeros, your step number 1 will be find the midpoint between the zeros. So find x in the middle of the zeros, or the x-intercepts. Okay, so algebraically you will do it this way. X in the middle equals the average of the x-intercepts, so 3 plus negative 1 divided by 2. So that would be equal to 1, so 2 over 2 or 1. Now what would the next step be? Think about it this way. I know the vertex will be somewhere in here. Well, because I know that A is positive, it is most likely actually somewhere below the x-axis. But I don't really know how far I can go in here, all right? So what can help me find what the y value will be, right, at the vertex? Well, I know what the x-coordinate will be at the vertex. And I know the equation of the quadratic function. So that leads me to believe that my next step must be finding the corresponding value of y at the x at the vertex, right? So that means that we are finding y at x equals the middle of zeros. Okay, you can call it midpoint as well, right? So here goes our second step. We're going to write the equation, which is y equals x squared minus 2x minus 3. And we'll say that when x equals 1, x squared would be 1 squared, minus 2 times 1, minus 3. So that's 1 minus 2 minus 3, or negative 4. So we'll say that the y-coordinate at the vertex must be negative 4. So here we are. I'm going to eyeball this again. There is negative 4. And I know that the vertex is exactly here. Now that I know where the vertex is, I can simply apply the step pattern. So always remember that you have to go over 1 horizontally and then up 1, because the step pattern is here according to this equation, since a equals 1, right? So the step pattern would be 1, 3, 5. So you're going to go over 1, up 1, over 1, up 3, and so on. So here I am, over 1, up 1, over 1, up 3. See, I hit the x-intercept. And over 1, up 5. I'm not going to worry that much about this section. So with this, I got one arm of the parabola. Similar to this, I go over 1, up 1 here, over 1, up 3. See how we hit the x-intercept? And bam, we're done. Okay? So, if you think that this made sense, then you probably want to try to do the next example on your own. Just stop the video and try it on your own. In the meantime, I will continue explaining it. Okay, let me draw the boundaries here. Okay. In the next example, we have y equals negative 2x squared minus 28x minus 96. So let's get graphing here. So remember that our step number 1 is take out the greatest common factor if necessary. Now remember that in this case, we have y equals negative 2, and then we have x squared minus 14x, and negative 96 divided by 2. Remember, 100 divided by 2, 50, but then you have 2 fewer, so 48. And that would be a positive here, because we took the negative sign out. Okay? And now we are thinking, can we, and I don't know if any one of you is thinking that, can we take this one out, or can we make this disappear? That can disappear when you have y in here. The y won't allow it, okay? But when you have an equation, if you had a 0 here, that is possible, yes. But do not cancel the negative. That will tell you the step pattern. And we're moving on to the next step now, which is we must factor. So the factored form of this equation will be two numbers that add to 14 multiply to 48. And I would say 6 and 8. So we need to know the zeros, which are found by making each factor equal to 0. Remember that. And we're going to say that the zeros are at wherever x plus 6 equals 0, so x equals negative 6, or x plus 8 equals 0, which means when x equals negative 8. Once we find the zeros, we need to know where the middle is between them, right? Because the middle will be the h value. And the middle is just the average of the x-intercepts. So we go negative 6 plus negative 8 divided by 2. So that would be negative 14 divided by 2, or negative 7. So with this, we found the h at the vertex, so the x at the vertex, or the h coefficient. So we're going to say that so far we've made a lot of progress. We found that the intercepts are at negative 6 and negative 8. So I'm going to plot them down here, and I'm going to go here by 2, 4, 6, 8. Okay, and we're going to say that between negative 6 and negative 8, we must have the midpoint in here, negative 7. That's where the axis of symmetry for the parabola would be. Okay, and now we have to find where the vertex is. Remember that our step pattern is already ready and waiting for us. Okay, so we don't have to worry about it. So the step pattern would be negative 2 times 1, negative 2 times 3, so I'm multiplying by 1 through 5, right? And negative 2 times 5. So in other words, we're going to have negative 2, negative 6, negative 10. So our step pattern here will be negative 2, negative 6, negative 10. And we're going to say that, okay, let's find the vertex, or the y-coordinate of the vertex, and be done with it. So the y at the vertex, we're going to say equals the value of the quadratic function at h equals negative 7. So it would be negative 2 times negative 7 squared. Okay. You can use the factored form as well, actually. The only reason I prefer to use the standard form or the given form is to avoid making any mistakes, because it's a given form, and sometimes if you make a mistake in here, that can lead to another one in the in finding the value of y. Okay, so but just so you know, you have that option as well. Squared minus 28 times negative 7, and then minus 96. Okay, so negative 1, positive 2, and then that would equal, I'm just trying to do some mental math in here, so that's negative 2 in here, and this would be times negative 1, positive 2, and this would be times positive 1, positive 2. Okay, so that means that the value of k would be positive 2. So we're going to say that the vertex is at negative 7, positive 2, and I'm going to let this be like here, 1, 2, and the vertex will be right here. And this point here actually will be negative 7, positive 2. And the parabola obviously will up and down because of the step pattern. So from positive 2, you're going 2 units down here, right? 1 over, so negative 7. From negative 7, 1 over, so you are at negative 6. Then you go 2 down. You see how the x-intercepts are there now, right? Exactly where we found them algebraically. And that's how we find, or how we graph the equation of a quadratic function by using the x-intercepts. So just to recap one more time, so far we have learned how to find the zeros of a quadratic function by using the x-intercepts, by using the factoring method. And then we found that, we spoke about the difference between an equation of a quadratic function and the equation of the zeros of a quadratic function. Okay, and we learned how to graph a quadratic function by using the factored form of it, or the zeros of it. So you have some independent practice that you can work on if you wish. I would strongly encourage you to do this example on your own. And the equations, they start very easy, and then you can move on to some more interesting examples. But this is it for today, and I hope all this made sense, and I hope you enjoy your practice.